I would like to welcome you all in the fifth Sports Analytics workshop. This is the first virtual due to the COVID pandemic. And of course, the aim of the workshop is to continue in the next year, again, going to live. Maybe we'll have some virtual versions of it, because I can see people that are interested to attend by distance. As I said, this is the fifth meeting. This year we changed also the dates. Usually the workshop was held on November, but this year we changed it to May. And the reason is dual. First of all, November was a very busy period for us here in Athens. And secondly, the weather is better on May. So in the future meetings, hopefully you will be able to enjoy also the weather if you visit Athens. For this year, we have about 18 talks. Some of them are very methodological, others are more applied. It's a mixture as every year. People that they have attended the previous year, you should know what is the style of the workshop. And the first session is more related with football. And the first speaker is Christophe Ley from the University of Ghent. He is going to talk about the probabilistic final standing calculator, a fair stochastic tool to handle abruptly stopped football seasons. So I will give the teams to Christophe. Christophe?
Okay, thank you very much. Now I can indeed unmute myself, and I should also be able to share. Yes, can you see my slides now?
Yes.
Okay, perfect. Then I shall start. Well, first of all, I would like to thank Yanis Dimitris and the organizers a lot for inviting me. It's a pleasure to be here for the first time at this Athens organized workshop, and I'm glad to present my work about the probabilistic final standing calculator. This is a joint work with my PhD student Hans van Eetvelde and Lars Magnus Wattem from Molde. So I think you all remember what has happened last year. When the coronavirus started, all the sport activities had to be ceased. And there was a big uncertainty because the leagues had to be stopped, and it was not clear at all if they could resume or not. Afterwards, well, we know now that certain leagues resumed, but others not. But at that moment, of which this picture here is taken, it's from the French sports newspaper L'Équipe, March 15th. There it was a big question: what happens with the season? Let us remember a little bit what has happened exactly. So the Dutch Eredivisie was the very first to declare officially its stop on April 25. It was then followed by the French Ligue 1 on April 28 and the Belgian Jupiler Pro League on May 15th. Other leagues, like the big leagues, the Bundesliga, Primera Division, Premier League, and the Serie A, they resumed to play, the Bundesliga being the first one. A main question, of course, is if a season had to be stopped abruptly, how do you then evaluate it in the best possible way, meaning in the fairest possible way? How did the three leagues that I just mentioned handle this? Well, in the Eredivisie, they declared neither a champion nor relegated teams. However, they chose their representatives for the Champions League and the Europa League for the next year on the basis of the ranking of March 8. The Jupiler Pro League made a similar decision, but on top of this, they also declared Club Brugge champion. And in France, they declared everything, so also relegated teams. Everything was declared based on the ranking when the league ceased to play. Well, it was a weighted ranking because not all the teams had played the same amount of matches, so it was the ratio of points per, with an R missing here, match. And well, this has given rise to quite some anger because look here, this was the final ranking of the League 1 when it had to be stopped. So here you see the points per match. And well, here it's all this here is very, very close. So between 6 and between 5 and 10 or 11 even, this was a really, really close call. And especially Lyon was unhappy. And you can also understand it if you look at the points that these teams have earned. They're all close together. And by just stopping the season, it is also unfair in the sense that, well, if there were teams who still had easier matches that were to come, well, they were likely to gain more points than teams who had matches against the top teams that were still to come. And not accounting for this was perceived as quite unfair by those teams like Lyon, for instance, who then could not take part in the European competitions. So that raised a scientific question. How can we find a fairer way to evaluate the seasons? In the literature, there was no real response to this before 2020. Except for in cricket. In cricket, there was actually a method when a single match had to be stopped. They have the Duckworth-Lewis Stern method that says, okay, how should you evaluate an early stopped match? But a similar question has never been treated. So what I did with my PhD student Hans van Eetvelde, we did this quite early in April, May. We made a statistical evaluation of the Jupiler Pro League, which we published in the Belgian newspaper Het Laatste Nieuws. Guillaume 2020 proposed an able-based approach in the newspaper The Times, and other approaches have also sparkled, such as those by Lambers and Spieksman, Chateau, Gorgi, Koopman and Lit. So of course the literature has been filling up because there was this question that people tried to answer. And following up on what we did for the newspaper, we developed it into a full scientific paper by adding also Lars Magnus Wattem to the picture. And in the end, we then proposed the probabilistic final standing calculator, which is currently under revision. So what is the idea of our PFSC? Well, we assign to every team a playing strength that is estimated on the basis of all the matches played that season. And to this end, we are using the bivariate Poisson model. And especially to the people, to several people present here, it is no surprise that we chose the bivariate Poisson model. It has been popularized, in particular by the paper Kalis and Soufars 2003 for modeling football matches. So we denote YIGM, the number of goals scored by team I versus team J during the match M. So we have in total N teams and M matches that are played. And their average number of goals, or the expected number of goals of team I against team J in this match is denoted by lambda IJM and lambda GIM. And then the joint distribution as given by the bivariate Poisson model corresponds to this formula that we see here, where lambda C plays the role of a covariance parameter. When lambda C is 0, this last part here disappears, and we simply have the product of two independent Poisson distributions. Now, what is crucial here during the modeling is that the strength parameters, they are obtained by this equality here. So the logarithm of lambda IGM corresponds to this here. Beta 0 is an intercept term that gives us the basic number of goals that we expect if both teams are equally strong and one plays on a neutral ground. Then here we have the strength parameters of the different teams. It makes sense to look at the difference of these strength parameters to model the expected number of goals. If Ri is much bigger than Rj, well then you expect that team I is going to score many more goals against team J. Plus we have here this home effect parameter that comes into play if team I plays at home and otherwise not. And then over a period of M matches, well, the playing strengths, they are estimated by means of maximum likelihood. And so here we have the M matches, so we take the product of these of the formula where YIGM, small YIGM and small YGIM were the actual scores of that given match. So we estimate all these parameters on the basis of all the matches that have been played till that point in the season. So why this model in particular? Well, it was proposed the very first time initially by Maher in 1982. And the superiority of the bivariate Poisson as compared to other models has been further underlined in a study that we did that we published in a paper from 2019. It is extremely good for predicting results. Now, how do we obtain the final ranking from this model? How do we go from the model to the ranking? Suppose that now we have estimated all the parameters, the strength parameters, the intercept, home effect, and the covariance parameter after X matches played in the season. Now, what we do is that we simulate 100,000 times the remainder of the season via this model. This is not difficult. You have the bivariate Poisson distribution. You can simulate the results from there. Then we take an average over these 100,000 simulations. And so for every team, we are getting the probability to reach every position. Because, yeah, every time that we have a simulation, we get a final ranking. And then we can get the probability, how often has a team been reaching rank 1, 2, 3, and so on. And this is why we call it the probabilistic final standing calculator, because we are calculating the final standing, and it is associated with probabilities, hence the name. And it is fairer because it does take into account matches that are still to come. Since we are simulating the remainder of the season, we are actually looking at the matches that are still to come. And if you had to face stronger opponents, well, this will reflect then in the simulations. The logical question is, how good is our PFSC? What we did is we compared it to two larger models. First, we took a similar model that was also based on results within the season, but we did not only look at matches in this season, but also the season before, so to have a longer training period. And we also gave more weight to more recent matches to really have the momentary performance of the teams. And second, this is where this is the model that was proposed by Lars Magnus Vattum. This is a model based on plus-minus ratings that actually does take into account the players that are present in each team. So we have two richer models, one based on 2 seasons and more weight to more recent matches, and the other one based on the players present in each team. And how did we compare our PFSC to these richer models? Well, we made an evaluation on several previous seasons from the big leagues. What we did is we made their virtual stops at various moments in the seasons. We simulate the remaining matches, and then we compared our prediction to the real final standings, since we knew that, okay, these were the final standings that had occurred. Little remark here, we deemed that it would make little sense to make a prediction, for instance, last year for the Bundesliga, and then check how the Bundesliga ended, because you cannot do this. Under Corona circumstances, there is no real home effect. Everything changes with players that are not allowed to play, so we cannot really compare a prediction and verify it with the Corona-related results. But the reasons before, it's perfectly fine to make this comparison. How did we do the comparison? Well, we used two metrics. First, on the individual match basis, we used the famous rank probability score that is defined like this. So basically, this is an L2 loss where we are comparing for every match the predicted probability for each possible result, outcome, home win, away win, draw, to the this is xj is the predicted probability to the actual result. Oj is the probability of the real result. So it's either 0 or 1, because of course we know what is the correct outcome. So here we can then check for which model the error is bigger over the matches. And we did the same on the final standing. So in a recent paper that just got published now in the Journal of Sport Analytics with Klaus Ekström, my PhD student Hans, and Ulf Brefeld, we have proposed an extension of the RPS to an entire tournament prediction, which we call then the tournament rank probability score, TRPS. So it's the same idea. You predict the ranking with associated probabilities, and you then compare the predicted probabilities XRT to the actual probabilities, where again it's a 0-1 outcome. And of course, also here you want this TRPS to be as low as possible. So here are the results for the 5 big leagues, including France also. What you can see here in black, this is our PFSC. In the red is the richer model that takes into account also the previous season. And in blue, you see the plus-minus ratings. What we can see is that always, and this is not unexpected, see here in the bottom, you see the number of matches that where we stopped virtually. So if we stopped before half of the season, that makes anyway little sense. But we wanted to see what was the outcome, and we could see that when we stopped before half of the season was played, then the other two models were better. But would you evaluate a season when less than half of the matches are played? Not really. So that's why we then, it's rather from here on that one has to, from the middle point on, that we should look at the results. And from there on, we see that the PFSC has caught up to the others. And there is no clear trend. Sometimes one model is better than the other model is better. So on average, it does as good as the richer models. This is for the RPS match-based, and now for the tournament prediction, it's the same picture. We see again that all the models are quite close one to each other, and we don't really see a difference. So this is the validation that our PFSC is doing as good as the richer models, but it has the advantage of being much simpler, requiring way less information than the richer models. And so this is why we propose this as our model to go. Now let us revisit the League One in 2020. So first of all, these were the estimated strengths. So you can see PSG at the highest, Lyon had the second highest estimated strength. So these are the results here. And from this, we can then get our probabilistic final standing. We can see that PSG was 100% sure in all situations they came out as first. Then here we can see Marseille, well, they were definitely the favorite for the second spot. And then we can look at Lyon, those who were very unhappy. Well, they had actually a quite high chance of ending on the 5th position. This is very interesting because they did not end up 5th. They ended up 7th according to the decision that was taken. But from our probabilistic perspective, they should have ended as 5th. And well, if we do a comparison, this is the final standing as it had been obtained, and this is the expected rank from our calculation. So if we look at average of all the ranks, this is what we get: PSG, Marseille, Rennes. That's the same as here, but then it's here. Lyon is a big difference. They are now 5th here. On the bottom, relegation, nothing happens. This is the same here and there, but we can see quite a strong difference for the teams playing in Europe, which shows that perhaps it was not the best strategy to only look at this ratio of points. So, as a conclusion, the PFSC is a fair stochastic model that allows us to evaluate abruptly stopped seasons because it takes into account everything that is still to come. It simulates the season, it simulates what we haven't seen yet, and so it is a stochastic tool. It allows leagues to take individual decisions. Yes, because in the end, look, this is what you get here, these probabilities. From these probabilities, the league can make their own decisions. They could, for instance, say, okay, teams are relegated if the chance for them to be on the 2 last places is above 60% or is above 70%. That's a decision that they could make on this basis. There's the full picture. The same holds for the European Cup. They could say only if they are above a certain amount of percent sure to be representing the country next year, then we declare them as representative. And the same rule could be done for the champion. So this is why we believe that this can be certainly a nice alternative to simply these points per matches that really created a lot of anger among the different teams. And what you can also do, you can build up a compensation fund by this strategy. So if we denote PI, the prize money that you get if you reach rank I, then for instance, in our calculation, Marseille would have received this prize money. Yeah? So they had 77% chance of being second, 18 third place, 5% fourth place. This is the prize that they would have received. But in reality, they did receive this prize if we were to look at this ranking. And so you could think of a compensation fund if this was done. So suppose that you do not want to build your the result on this probabilistic final standing. You say, okay, I want to stick to this decision here because this is what we want to go for. Well, then at least you could give financial compensation to the different teams. And you can then calculate how much, for instance, Marseille would have to pay back in the compensation fund, and then see if and other teams would then receive money out of this. So this could be another way of making it somehow fairer. If you don't go for such a ranking, well, at least you could think of such a compensation fund. So a lot seems possible by this type of approach, and I'm really saying all ideas are most welcome. We did this quite fast last year because we had to come up quickly with something new when we were asked about how fair it is, and we wanted to give this evaluation of the Belgian Jupiler Pro League. But this is, I think, an interesting research avenue where we can further think, okay, perhaps we could use different types of models, bearing in mind that they should not be too complicated because we don't have too many data points available within a season. So I encourage everybody to think about this, and all ideas are absolutely most welcome. Okay, I thank you very much for your attention.
Thank you very much, Christoph, for your nice talk. Are there any questions from the participants? You can raise your hand if you want. Just a minute, I think there is a question in the chat. Christoph, for you, can you elaborate on the estimation of the procedure you used? Did you use GLM machinery?
Okay, yeah, because I cannot see the chat, so I cannot read from there. Okay, well, machine learning, no. So there is no machine learning in this here, because well, all we did was really let me go on this slide. We used this model. We estimated the parameters by means of maximum likelihood. So it's all based on statistics. We also can have the uncertainties of the different parameters. We could also build the uncertainties of the ranking. So it's purely statistical, and afterwards we use simulations to come to our result. For this problem here, in general, if we have a lot of data points, then I think, of course, machine learning is very interesting. Here, I'm a bit uncertain if machine learning would make sense, simply because, well, if it's within a certain season, for every team, you just have, if it's stopped after 28 matches, for instance, you just have 28 data points per team. This is not a lot. You have to estimate these strength parameters here. So I'm not sure if machine learning is the best way to address this particular problem here. In general, yes, and I mean, for instance, we are now also working on the prediction for the World Cup. Well, there we do have a lot of training data of all the previous World Cups. So there, definitely, yes, we are using machine learning for that purpose. And that's also what I would recommend. But here, for this small amount of data, I think you have to be careful, because you might really run into a problem of not having enough data for the number of, for the machine learning to run.
Any other questions?
I see one raised hand.
Yeah, it's the same.
Ah, okay.
If there is no other question, I have one or two questions, Christoph.
Yes.
The first one, I didn't see any inflation for the draws. Have you checked if there is underestimation of the draws with the model? Because in most leagues,
yep,
it seems that there is some kind of underestimation on that.
Yes, so that's one of the things. We haven't checked that yet. But we have been thinking if we should also include this. This is part of the further ideas that I think one should definitely go for, to use also, like you use this model for 0-0-1-1 or for the small matches. That is a way how you can enrich the model. Still, bearing in mind that we should not have too many parameters here for the estimation purpose, but it's definitely something that we should also look into.
My second question is that here you use the common abilities for home and away. Am I right?
Yes, exactly.
Not attacking and defensive abilities.
No.
But because I was doing something organizational, I didn't catch the other two models that you are considering. Can you explain again what were the other two models?
Sure. So the one model is similar to this model, but we used 2 seasons, also the previous season for the training, and the second model was based on plus-minus ratings. So there you of course have in the plus-minus ratings you have attacking skills, you have defensive skills, you have all types of skills of the individual players that are taken into account. And so because we really wanted to see a a model with a lot of parameters like that one, a lot of details, what it would give, and we could not see that there was a difference in performance.
Okay, can I see the graph? Because actually on Wednesday in the course I'm saying the same thing, that the vanilla model, the simple model just with abilities, after mid-season is good enough. It doesn't need any information from the previous years or a lot of covariates, which is amazing because the model is very simple. So this graph actually confirms what I have seen and what I'm going to say. There is another question from the same person. I'm not saying his name because he's using the email and I don't know his name. Did you consider zero inflated bivariate Poisson? No, without. Christoph replied without inflation. Okay, so this question was already tackled.
Oh, but I just can come back on this, that the zero inflated Poisson is also an interesting model. I also was thinking, of course, you can also go for the negative binomial as a complete alternative, or something that I think has never been looked at in the football world is the Poisson distribution, Conway-Maxwell Poisson distribution, an extension of the Poisson model. But I think
Christoph, actually, with Niall Friel, he's one of his students. He did an excellent work on that.
Really?
But he left Dublin, so the paper was never published. It was almost completed. So especially in some championships, it behaves very well because there are some exceptions that they have other dispersion, and the Poisson also handles other dispersion. I think there is another question. Let me see. Let me check. Yes, from Yannis Kostadopoulos. Did you take into account the reductions in the player performance, attacking and defensive skill due to the pandemic?
No, not at all. So I'm happy for that question because I really want to make this clear again. What we did here is we wanted to evaluate the season in the fairest possible way, as if it was played in the same way without any pandemic effect. That's very important because there will of course be reductions, and I think it is super hard to it would be super hard to model this. This is also why in our comparison we really based ourselves on previous seasons, and we did not say, okay, the Bundesliga has played till the end. Oh, let's see how good our model would predict the remainder of the games. No, because we strongly believe that if you would really have to find a new way to incorporate this drop in performance, and you have no experience in how it would drop so far. So I would not know how you could model this in a really sound way.
Yes, I agree. It's not easy at all. So let's thank Christoph for his wonderful talk and very hot because of pandemia. And let's continue let's continue to the next speaker. Next speaker is Abdullah Zafar from University of Toronto, Canada, and he's going to talk about characterizing team passive behavior in elite football, a topological approach. Hi, Abdullah.
Hey, can you hear me?
Yes, very well. How is the weather there? Here is 30 degrees.
It's still a bit chilly, but it's getting better, so I can't complain. Yeah. Okay.
For your talk.
All right, great. We can see my slides now.
Yes.
Perfect. Okay. So yes, thank you very much for having me here. So yes, the talk is characterizing team passing behavior in elite football as a topological approach, right? So we're going to look at some like applied physical or mathematical models just to see how we can analyze passing behavior. And so just a quick overview of what we'll be covering today. Just a quick introduction on like how historically passing analysis has been done in football. What are some of the limitations of it? And then what's our proposed extension or expansion on those models? Then moving on to actually what we did methodologically. And then finally, we're going to apply those topological methods to the World Cup. And specifically, we're going to look at the French national team and see how they performed and what we can tell about their passing behavior and style over that tournament. So passing analysis, what do I mean when I say passing analysis? Essentially, we're going to be using this mathematical structure called a graph. And so it's weighted because it depends on the number of passes being played between players. And it's directed because the direction of the pass matters. Who passes to whom is important, right? The passer and the receiver. And so this is the typical thing that's used to do passing analyses in football currently, right? And there's many studies on this. So the graph is essentially, you can look at it as an actual matrix, right? Where each column, each row is a player or is assigned to a player. And so the entry, for example, in the first row, third column would mean the amount of passes done from that first player to the third player. And so why is it useful? Well, there's different properties of these graphs. For example, the density, the distribution, the clustering, and these tell you specific things about the network, the passing network. The density might tell you how much passing is going on, right? A possession-based team, you might expect the density to be higher compared to a team who doesn't hold possession very well. Distribution, right? It's almost in the name, like how well distributed the passing is. And then clustering, again, are there like groups forming within these passing networks? And so again, this is the current kind of methodology when it comes to doing passing analysis in football. Now, what's the big limitation here with graphs, right? The big limitation is the graphs are only capturing dyadic or pairwise relations, right? So you're only looking at a single interaction at a time. And what that means, especially in the context of football, is that you don't have these larger tactical units or cliques, right? Sometimes you call them passing triangles, or it could be more than 3 players, but you cannot capture, those are not inherently captured within a graph model because graphs are only looking at pairwise relations. And so a way to, maybe another analogy to this is, for example, in a graph, right, you can only look at 3 individual two-way phone calls, but you cannot model a 3-way phone call, right? And so, of course, the dynamic of those 2 phone calls are completely different, right? So in the same way, yes, in a graph, you can measure these pairwise interactions in terms of the passings, but you can't capture these larger tactical units, and you can't capture those larger dynamics that are happening in the passing. So how do we get around this? Well, the solution is to use simplices and simplicial complexes. So just a quick overview, simplicial complexes. Basically, if you have your set of players, right, you have n number of players in your team, you have a set of players, and you have your adjacency matrix, you can define a simplex basically by saying what is a complete graph within your overall graph. So just looking over here at the diagram in the top right, over here, when you have A, B, and C only passing to each other, but you have no complete triangle, right? These are just essentially 2 pairwise interactions between the players. As soon as A, B, and C form a complete triangle, right, this is now a simplex, right, within the complex. And then, of course, you can keep adding players onto this. And as long as all the players are all mutually connected to one another, right, this becomes like a clique or a simplex in the complex. And so the reason, right, this particular simplicial complex is called a clique complex just because we are finding these complete graphs or complete subgraphs or cliques within our network. And so just a quick note, we still, like looking at this diagram in the bottom right, we still keep the underlying graph structure. So it's not like we're losing any of that information. It's just that on top of that graph structure, we're kind of appending these triangles and these tetrahedrons and these, you know, higher dimensional tactical units that are being formed due to the passing. So we keep the information and we're just appending onto it. Now, why even go through all this trouble? Like, what can we tell from creating this kind of simplicial complex? And so one of the main kind of ideas is to use homology groups. And so what those are is they describe different dimensional holes within our simplicial complex. So zero-dimensional holes are looking at disconnected players. The one-dimensional holes are looking at cycles, right? So the cycles, for example, here are what are highlighted in red. And then two-dimensional holes, which we didn't actually apply in this kind of project, but two-dimensional holes are describing larger structural voids, right? So it's just essentially the larger the dimension of the hole, basically the larger the void or kind of structural disintegration you're picking up. Again, in the context of football, how can we contextualize what these holes would actually mean? When it comes to zero-dimensional holes, again, you're talking about disconnections, so that's pretty straightforward. Are players connected or are they not connected, right? Are groups forming in the team that are connected, or is the entire team one unit? One-dimensional holes are a bit more interesting, and what they're describing, again, are these cycles, but in the context of football, it's essentially, if this cycle is forming, you can infer that to be where the ball is being played through, or areas of the pitch or areas of the team that the team is playing the ball much faster. It's essentially a faster buildup versus a slower buildup in those areas, because when there is no hole, because those interactions are forming, and essentially the team is able to keep possession in those areas a bit better, or intentionally or unintentionally. So once we figured out the homologies, the next step is to look at persistent homology. And so persistent homology allows us to break down our network structure into several layers or several levels, so that we can find like the overall team structure all the way down to like micro level like dynamics that are happening between players. And so how we do this is, first we create some kind of filtration. In this case, we create a weight-based filtration. So basically you normalize the matrix and you invert it. So in this case, the labels here, meaning, for example, the 20% here are referring to player like passes that are in the top 20 percentile, right? And then same going all the way down, 100% would mean the lowest number of passes. You know, so essentially you've filtered all the way down, so you have all the passes in your network or in your matrix. And so we call this an inverse Vietoris-Rips filtration on a network. Then you want to compute the topology at each step. So we're going back and we're going to be computing where are those cliques forming, where are those holes forming within each level of these of this filtration. And finally, we can encode all that information as a barcode. So in this case, again, we're only looking at dimension 0 or dim 0 and dimension 1 or dim 1, right? And so just reading what this barcode might tell us, in this case, like with this sample network here, dim 0 is again looking at the connectedness of the players, right? So at 0%, essentially when, you know, there's no passes being formed, we haven't really filtered any passes, you have all 11 players because they're all disconnected, no passes are, you know, considered. Then as the filtration increases, we see how the number of connected components decreases until eventually at 100%, you know, all the players are connected with a pass, right? There are no disconnected components. So that's how we would understand dimension 0, right? How you're going from 11 players all the way down to a single connected unit as a team. And then dimension 1 is, again, the red cycles that are being highlighted. So we can see, for example, at 60%, we will see a couple of these cycles form. One of them, you know, goes away at the next level. A couple of them persist for some time. And so again, we're looking at the persistence of these homologies within our passing network, hence persistent homology. Now, imagine we did this for, you know, the passing network for a team in one match and a passing network for a team in another match. So how could we actually compare them if we have these two barcodes describing our passing network? So the first step is to actually encode these into just a real coordinate plane. And what the X and Y coordinates map to are essentially the birth index and the death index of a particular hole within our network, right? And then once we have it encoded in the real coordinate plane, we can use a simple optimal transport method. So in this case, we're using the Wasserstein metric, or it's sometimes called earth remover's distance. And what that means is basically you are creating two sets of points, right? Like one is the point and the point's projection onto the diagonal. And then you are minimizing the total distance between pairs. So you're finding the optimal distance or the minimized distance between these two sets of points in the coordinate plane. And that, that minimal total distance essentially becomes the distance metric on the two networks or on the two barcodes. And so if we do this on multiple matches, then of course we can then start clustering matches or network performances together using this kind of distance metric. So again, the application aspect now. We went ahead, we looked at the World Cup in 2018, and we analyzed the 7 match performances of the French national team, right? So created the adjacency matrix, went ahead, computed the persistent homology, and then, here we actually computed the Wasserstein metric between the two and clustered the points accordingly. So interestingly enough, we found 4 clusters of performances. So France, essentially the first match France played with the final performance against Croatia, then another group match with another knockout round match, Peru and Argentina group match, knockout round match, and then the France versus Belgium game was almost like a standalone performance, right? It didn't cluster with anything well. And so, okay, this is very nice, but what does it really mean, right? Like how well does this really parse out styles, this kind of methodology? So, we can go back and we can look at the actual passing networks of, these performances and see how they compare with one another. And so, again, this was that first group here, Denmark and Uruguay, group stage match, knockout round match. And we're looking right now at the dimension 0 kind of structures, right? So we're looking at essentially the player interactions or the passing, the individual player-to-player passing. And so we see how the passing network itself reflects how, in these 2 matches, France was heavily reliant on the wide channels. Comparing that with the second group, Peru and Argentina, right? France was using these midfield pivots, and especially in this kind of like X'd out or crosswise pattern. Third group, France, Argentina, we see how they have this interesting structure of possession among the defensive line and then like playing it into target players. And then finally, again, France and Belgium looks completely different, right? It's almost like you have 2 disconnected components, almost disconnected components within the team. And so again, this is just stylistically thinking about why those performances, when we ran the network analysis, might have been clustered with one another. Moving on into the first dimension, right? Now this dimension 1 is again looking at cycles within the passing network. And so, okay, for France, Denmark, and France, Uruguay, right? This is the only 2 matches where you had 2 actual, main cycles forming in the team, and they're complementary with one another. So basically one cycle forming among the goalkeeper or defensive units, and then another cycle a bit higher up with the midfielders. Again, just, cycles referring to speed of play. So where we don't see cycles, we can assume that the passing connections are rather strong between here, or that, France was able to maintain possession in the areas where there weren't cycles. Where there are cycles, we can infer that, France played through these areas along these cycles, in a much quicker fashion. Defensive cycles in the next round, right? We just see how the cycles are forming along one half of the defense. In the third kind of section, we see, again, like skewed midfield cycles. So it's kind of like diagonally covering the team. And then finally in France and Belgium, it's again completely distinct from the other kind of performances in that it is like, one wing is completely cycled and then the other wing is, doesn't have any holes at all. So the final kind of piece here is to actually relate, what we're finding with these networks and how does it actually relate to some of the kind of maybe more traditional performance stats that we see. And so in this case, we're going to be looking at this last row here is going to be looking at what's called the attack origins. So looking at like percentage wise, right? How many times does a France attack from the left wing or left channel, the middle channel, or the right channel? And so, okay, when it comes to that first group where they're heavily reliant on the wings, it kind of lines up with what we see with the attack origins. When it comes to this kind of build up through these midfield pivots across, we see how this out of the four groups has the most maybe distributed attack origin. And then when it comes to these last two groups, because of the skew, we can see how the attack origins are biased towards one side, even though they use both wings. The interesting thing about the last two is how, in this case, remember thinking about the cycles form on kind of like skewed or biased toward the left-hand side versus this performance where the cycles are skewed or biased towards the right-hand side. Yeah, they both have the same attack origin, right? And so all it goes to show is how, like just looking at attack origins doesn't necessarily tell you anything about the manner in which those, attacks are built up, right? Whereas when we look at the actual cycles, we can say, okay, they attacked down the right channel, but in one case, it was reliant on much quicker counterattacking movements because of these cycles. And the other one, it was more of controlled buildup or controlled attacks through the right-hand side. And so that's just a quick way we can use to kind of connect the actual passing behavior with tangible performance outcomes, as, typically measured. And so where can we actually take this? One thing which we kind of started, but it definitely needs more fleshing out, is opposition analysis. So this is actually one match we're looking at and we focused on because it was such a standout match, France and Belgium. And we were looking at, okay, in blue, as we've seen before, this was France's kind of first dimensional holes. But then in orange, right, we see how Belgium, when we did the same analysis, when we calculated like where Belgium's first dimensional holes or cycles are forming, we found it was like, this kind of orange, like that orange cycle. And of course, we flip these graphs, right? So they're actually, France is going one direction, Belgium is going the other. And so it's just interesting to see how these are complementing one another. And so, of course, opposition analysis, we have to start looking at, okay, was France affecting Belgium? Was Belgium affecting France? These kinds of questions. Is it always complementary? How does this affect performance outcomes? These kinds of questions. Kind of related to that is also doing a temporal analysis. So, looking how France may have evolved or changed back and forth between styles over the course of a match. And so in that case, it'd be very simply just doing the same analysis, but breaking the match into periods and then doing the same clustering or Wasserstein metric on different periods within the same match. And then finally, of course, because we want to apply to actual training, so looking at physical and technical implications, do certain play styles, cost more physically or have some kind of technical implication. So that is actually all for this presentation. Of course, some references like, about the topological analysis, my contact and my colleague's contact who I worked with this on. And thank you for listening.
Thank you very much, Abdullah, for your excellent talk. Actually, I was ready to tell you that it's time to finish, but I just saw the references. Any questions for Abdullah for his talk? I think there is a question. Just a minute. have you considered the effect of the opponent team pressing pressure on the topological properties?
Yeah, so this it's a really good question. So like I said, this is something we're working on currently. The first step for us was to, because we're looking at the entire match, we're just looking at the entire match performance. And so we haven't really been able to break it down play by play yet, right? So what we have to do is kind of these two steps as the next step. First, we have to do a temporal analysis to see, okay, how are these cycles forming over the course of the match? And then we can see, okay, like what was the, I guess, opposition influence on the forming of the cycles? Like, was it self-initiated or was it actual, like a reaction to what the opponent was doing or how the opponent was playing? Right.
Another question is the following: can't we arrive at the same results by simply observing the weight of the edges in the directional graph of the passes? What is the difference on your approach with this simpler approach? This is from Amphimios Tsakaleris.
So can you just look at the weights of the edges? No, we can't just look at the weights of the edges, simply because if we, I mean, okay, first of all, technically, all we're doing is this graph. It's not like we've added any information from this graph, so all the information is technically derived from the weights of the edges, right? The point, though, is, for example, we can't just look at the weights of the edges and form the cycles themselves. Because you are going to miss out on, like, you won't know whether there are cliques forming around the cycles or whether the cycles are isolated, like whether the cycles are a true cycle or whether they're simply an extension of, like, or whether they're actually a clique filled in. The second point, that you can't just look at the weights, or you have to kind of go through with the entire homological analysis, is because you won't know when those cycles formed. Right, so you won't know whether the cycle actually lasted for a brief second, or whether, like, you know, as in whether they're a small feature within the network or whether they're an actual persistent feature. This we can't just pick up just simply by looking at the weights, unfortunately.
Abdullah, one last question from me. I think this work is very useful for the team managers. So if they have, they can have this information from the opponent, maybe they can adapt their strategy and break some of the strategy of the opponent. Am I right on that?
Yeah, exactly. So again, this is as it is, it's probably only useful as like a kind of like, you know, maybe after action review, like after the match. But once you actually break it down into a temporal analysis, expanding it into that realm, that would be the idea, right? To be able to see when certain strategies are being adopted or not adopted, and then maybe exploiting, if you were analyzing the opposition, exploiting these cycles and where they're forming within the opposition, right? Because you can use those cycles or holes as a way to break up the team, right?
Okay, thank you, Abdullah, for your excellent talk. Let's move to our next speaker, who is Marius Otting from the University of Bielefeld, Germany. And he's going to talk about tracking data, analyzing football tactics using high-frequency tracking data. Hi, Marius.
Yeah, hi.
I hope next year you will be in Athens.
I hope so. Yeah, I will share my screen. Can you see this now, the slides?
Yes.
Okay. Okay, great. Yeah. Hi, everyone. And yeah, thanks to you, Yanis, and Dimitris, and to all the Athens University Sports Analytics Group for inviting me and for having me here today to give you a quick overview of some of my work here. So I will today talk about analyzing football tactics using high-frequency tracking data, which is joint work with Dimitris. And yeah, I will start with a quick overview on sports analytics in general and sports. So I mean, as we all know, it started like a bit in the US, actually in baseball, where people took a look at massive data sets and Yeah, thought that it's a good idea to use data to aid decision making. And nowadays, I mean, lots of the major leagues in the US, like also in the NFL or in the NBA, teams are using tons of data. But nevertheless, it's not only the US or the teams in the US who use such kind of data, but also in European football. So, for example, one headline here says that Manchester City, that they launched an AI football competition together with Google. Or in another headline, it is suggested that in the German Bundesliga, Bayer Leverkusen, that they're also using some kind of data analytics. And indeed, in Germany, Bayer Leverkusen, they are fairly famous for having a team of several data scientists who investigate data sets in order to aid the decision making of the coaching staff and of the managers. And yeah, if we think of data sets in sports, I mean, we can think of very different data sets. So for example, event data sets where all events are recorded in a match. So like every pass or every shot on goal. Here today, we consider a tracking data set. So here in this figure, you see like the soccer pitch and two teams and the ball. So the red dot here in the middle, this is the ball. And this is just a snapshot of our data. So all positions, so the positions of all players are here tracked multiple times in a second over the entire match. And this is the snapshot like right before the kickoff, so right before the match starts. And of course, we can also have a look at another snapshot like 1 second after this, where the first pass is played, where now the player down here has the ball and all players moved a bit. But of course, we can also like glue these snapshots together in a single plot and produce some kind of flicker, so some kind of animated figure here. This can be seen here in this GIF. So the speed here is a bit faster actually than in the actual match. But we see here that the black team, that they are in build-up play, then they lose the ball. And the blue team, then they play with much pressure on the goal, and finally they score a goal, and all players are running to the top left to celebrate their goal together with the fans. So this is some kind of a nice visualization one can create using such kind of tracking data here. But yeah, these tracking data has been considered in different sports. So for example, in US sports such as basketball or American football, but also for association football or soccer. As we've also seen in the previous talk, lots of different analyses exist. So for example, as we've just seen a few minutes ago, analyzing passing performance is something which is of course of great interest, or analyzing the formations of teams, or the space creation. So especially the latter point, space creation, something which experts on TV often discuss. So, for example, Thomas Müller from Bayern Munich, he's quite famous for being very good at space creation on the pitch. And there are lots of other studies using football tracking data, and there's a really nice review paper by Ghost et al. Published in 2020. And they summarize very different studies which have a look at football tracking data. Okay, so what are we going to do here today? So when we look at the existing literature, most of these focus on like certain events, but here we want to model like an entire match. So from the very beginning to the end of the match, and our main aim here is to like automatically detect a team's playing style. So when I say detect here, I mean like classify, to analyze or to automatically classify what kind of playing style a team had. So in the most simple case, you could think of maybe a team playing either offensive or either defensive playing style. And yeah, this could be of interest. Then, of course, if you link these classified playing style to some events which occurred during the match. So for example, if you could then consider this classified playing style, if you compare these to events in a match. So for example, that you can see, okay, when goals were scored or when goals were conceded, what kind of playing style had the team at that time point. And to investigate this, we explicitly take into account here the time series structure of our data set. So we will have a look at the data. So I mean, at the beginning, I showed some plots of our data here. Yeah, so the data set we investigate here is some kind of tracking data which we have obtained from one match. So unfortunately, only data from a single match, which has taken place in one of Europe's top 5 leagues. And yeah, as we've seen at the beginning in the plot, we have the X and Y coordinates of all players and for the ball. And these coordinates are sampled with 25 Hertz. So we have 25 observations per second. And as a football match lasts at least 90 minutes, we end up with about 3 million observations then at the end in total. And yeah, if you have such kind of tracking data, one of the main first questions, of course, is, okay, what are we actually going to model here? And here we focus on the convex hull, which is created by all players, excluding the goalkeepers. We can see this here in the plot. So the convex hulls for both teams, so for the blue team and for the black team. And this measures, so the convex hull of the players, this is in the literature also referred to as the effective playing space, or short just EPS. And we consider the EPS here because we believe that it covers like several aspects of a match. So for example, it also covers the team formation, or it includes some information about the team formation because the EPS is basically calculated from the position of the players. The EPS is also related to the way that a team attacks or a team defends. And we can also link the EPS to events in a match. So for example, to goals scored or shots on goal to see how they were created. And we can have a look at some further plots here. So these are just, for example, snapshots here in our data set where we highlight the EPS, and the size of the EPS in square meters is then shown on the top right in each panel. In the first row, we see situations where the blue team is in build-up play and the black team is defending and just standing fairly compact on the pitch. In the second row, we have two situations where the black team is in forward play or in build-up play. And these situations are a bit different because here on the bottom left, we see that they are standing fairly compact on the pitch. And whereas on the bottom right in this plot, the black team, they are here in build-up play, but the players are like widely distributed across the field. And we can see this then, of course, also at the size of the convex hull, so at the EPS. Okay, this EPS is then, of course, observed like at every time point in a match, and we can have a look here then at this bivariate time series. And what we can see here from the plot is that, for example, at quarter to 3 here, at the beginning, it seems that some data points are missing there. So what's happening here? I mean, as we all know, in a football match, there are lots of breaks where the ball is out of play. So for example, if players are injured, and at these time points, of course, the players are also standing on the pitch, but the convex hull or the size of the convex hull, the EPS is then not very meaningful and not of interest to us. So all these time points where the ball was out of play, these are deleted, and that's why we see some space here between some bars in these plots. And what we also see here, based on this plot, is that there are like different phases or different periods in the match. So for example, at the beginning of the second half, we see that there's a period where both teams have a rather high value for the EPS, so where both convex hulls are rather large. At the end of the match, we see quite a bit of a different pattern where team A, so the blue team, has a larger convex hull, so a larger EPS than the black team here. And to explicitly account for these different periods in a match where the level of the EPS a bit changes during the match, this brings us then to the modeling framework, because to explicitly account for these phases where a team has a rather low EPS or a rather high EPS, we consider hidden Markov models, where we have like two stochastic processes. The one on the top here, which is denoted by Y, these are simply our observations, so the EPS. And since the size of the convex hull, so the EPS, since this is continuous valued with positive values, we choose the gamma distribution here to model this quantity. And here to account, for these different periods with like different levels of the EPS, we assume that the EPS is driven by an underlying state, which could here interpreted like the underlying playing style of a team. Again, in the most simple case, if we select like two states, this could be like a defensive or offensive style of play. And for example, if a team is in an offensive style of play, then maybe we observe larger values for the EPS, whereas if the team is in a defensive or playing a more defensive style of play, then we maybe observe rather low values of the EPS. And for the state process here, so for the unobserved playing style, we assume the Markov property, so that the playing style at time point t is determined by the playing style at time point t-1. And how does then look like if we fit like a very, very basic model here? So we then end up with a model with simply two states. This would be a very basic model where we have then two gamma distributions referring to the two states, where we have reparameterized the gamma distribution. So there are like different parameterizations, for example, with the scale and shape parameter, but since these parameters are not that intuitive to interpret, we use a parameterization here where mu is simply the mean and sigma is simply the standard deviation. And we fitted this model with two states to the data from the first team, so from team A, which was the blue team in the plots. And here we see, okay, we end up with two different states as we selected, and these two different states then refer to two different sizes of the convex hull, so to two different EPS means, where in state 1 we have a mean of 960 roughly, and in the second state we have a mean of about 1700. And the transition probability matrix here, which gives on the main diagonal here, these values 0.997, these in the top left, this is the probability for staying in state 1. On the bottom right, this is the probability for staying in state 2. And I mean, as we have a very high resolutional data set, it is very likely that a team will stay in a certain state simply because it's intuitively plausible that if a team is in a certain state, they won't change the state within a given second. So that's why we observe these high values here. But based on the parameter estimates for the gamma distributions in the two states, it's not that straightforward to interpret these results, or to turn these results into like practical recommendations for teams and managers on the pitch. And in addition, we also here in this model, in this very simple model, we fitted this two-state hidden Markov model only to the data from one team. But of course, on the pitch, we not only have one team, but we have two teams. So, and there might be some correlation between the EPS of the two teams. So we end up here with a bivariate model to also account for potential correlation between the EPS of team A and of team B. So we use a bivariate hidden Markov model then, where we allow for correlation in Y. So we simply allow for correlation between the EPS of team A and team B, and this is done here by using a copula. And just for illustration here, we use the Frank copula, where the dependence parameter is denoted here by theta, which can take any value between -infinity and +infinity except the 0. And now we're going to have a look at the results for this bivariate hidden Markov model, where we model additionally the potential dependence between the two teams' EPS. And we have selected 3 states here for our hidden Markov model. And here in this table, the parameter estimates are shown. And we see that here in the first 2 states, the mean for team A, so for the blue team, is higher. In state 1, we have a negative dependence here, and in state 2 and 3, we have a positive dependence. And also in state 3, we observe that the EPS for team B is larger, so the mean here is about 1,600 square meters, whereas for team A, it's only 1,000 square meters. But to be fair here, it's again a bit hard to really make sense out of these parameter estimates. So to interpret these results or these distributions without yeah, like having a look at the data again. I mean, we could also have a look at the counter plots, so at the fitted state dependent distributions here for state 1, state 2, and state 3. But what really helped us to interpret the states is simply to have, like, again, a look at the data and to decode the states. So we simply have a look at the decoded state sequence, so which is like the most likely sequence of states, so that at each time point we have a decoded state, and then we can simply look at all situations, for example, which our model classifies at state 1, and have a look again at the situations, how the teams like behave on the pitch. And we see here one example situation for state 1, where team A is in build-up play and team B is defending, but the convex hull for team A here in state 1 isn't that large. For state 2, we have a similar pattern, but it's still a bit different, of course. Here in state 2, also team A is in build-up play, but the EPS is much larger than in state 1. And in state 3, it's team B, so the black team here, which is in build-up play, and they have a fairly large EPS here. So these are the example situations based on the decoded states. And we can, of course, then with that in mind, we have like a better interpretation of the states. So state 1 and state 2 is like mainly team A in build-up play, just with a different size of the EPS. Whereas in state 3, this refers to team B being in build-up play. And we can then have a look again at the time series, which I showed you also at the beginning, but now color-coded here the decoded states. So we see here now in which time points which state was active, like according to our model and according to our results. And based on that, we can, of course, here, for example, compare with what kind of events happened in the match. So, for example, we could now have a look at, okay, when were the goals scored and what kind of state was active at that time point when, for example, the first goal was scored. And this can again be done like in an animated figure here. So we will now have again a look at the goal which was scored, which we also have seen at the beginning. So here team B is in build-up play, and on the top left we see the decoded state, which is now state 3. They're passing the ball and now they will lose it, I think, and the ball gets intercepted, and then team A is in build-up play, and the state, now the decoded state, now switches to state 1. And yeah, we know what happens next because we've seen this at the beginning. Now they're playing with much pressure on goal, passing the ball in the box, and then they score a goal. And the decoded state here, until the goal was scored, was still state 1. So based on this, like animated visualization here, we can directly see, okay, what kind of state was active when a goal was scored. Simply just as some kind of practically model check, so to speak. What we can also do with this decoded states is to simply check how much time is spent in each state. So here, what this little table shows us is how many consecutive time points the match was in state 1, state 2, and state 3. So these are the median number of consecutive time points which is spent in each of these states. And when we think back to the interpretation, state 1 and state 2 was team A in build-up play, and we see that the median number of consecutive time points in these states is lower than in state 3, and state 3 referred to situations where team B was in build-up play. So what we can infer from these results is that team B is a bit longer in build-up play, which means that or one interpretation or one reason for that could be that if team B is in build-up play, they are more likely to keep or more willing to keep possession of the ball and to be like in a small build-up play. Whereas in state 1 and 2, where team A is in build-up play, they don't spend that much time in these states, so they're maybe not willing to keep possession of the ball for a long time, but they maybe want to play more quickly towards the opponent's goal. So by putting more, or by playing with much pressure on the opponent's goal than compared to Team B when they are in build-up play. So this is also something which we could here infer from our model. Yeah, so this is pretty much work in progress here. So the model I showed you with 3 states here is chosen based on some model selection criteria such as AIC and BIC. However, in hidden Markov models, it's not always that easy to select the number of states. So if one has like a bit of an expert knowledge, maybe related to the teams which are participating here in the match, then one could also, for example, go for a larger model with, say, 4 or 5 states, and to check how these additional states could then be interpreted. One could also include some covariates. So, for example, covariates on the possession or on the position on the field. So something like the mean possession on the field of the team. And yeah, I believe that this approach, which I talked about here now in this talk, is really useful if you pool data from multiple matches, because then if you have like matches for one season for all teams, so for example in the Bundesliga then about 300 matches, and you fit this model to like 300 matches, you can really get some more knowledge or some more automatically detected knowledge about the opponent's playing style, because you then can simply check in how the next opponent, maybe if you analyze their playing styles, you can then, using this algorithm, you can see, okay, in what kind of situations led to goals which were scored. So you maybe don't have to watch like hours of videotapes, but can instead use these kind of data in order to see, okay, when the goals were scored in the previous matches, based on which state did they score the goal, and what kind of state was that, or what interpretation is related to that state, so to get an idea of how the opponent scores usually their goals. So this is something which could be used if you pool data from multiple matches and use this approach here. Okay, so here are then some references on the last slide, and yeah, thank you for your attention.
Thank you very much, Marius. There is a question by Mr. Kostadopoulos. If we see that the EPS variability shows, if we assume that the EPS variability shows the mobility between players, could we find a relationship between EPS and the expected goals, since the mobility is more likely to happen in the attacking phase?
Okay, so relate the mobility to the expected goals.
Yes.
What? Yeah, this could of course also be some kind of analysis one could think of. I mean, what I just briefly skipped here was that how goals were scored. That you look at such kind of sequences, but of course you can also like have a look at the expected goals and maybe check, okay, in these situations where the team has a fairly large expected goal figure, how was the EPS there, and maybe we see some relation that maybe I don't know, maybe that larger values of the EPS refer to a higher probability for scoring a goal, so to a higher expected goals number there. This could worth be investigating, I believe.
Thank you, Marius. Is there any other question for Marius? Okay, Marius, before we close for our first break, I have 2 questions. I wonder, the method seems quite computationally intensive for one game. And as you said, the aim is to implement this in many games. So what about computation in this situation? Is it going to be easy?
That's a good point. So what bit of helps us here is that the raw data set with the 3 million observations, it really reduces substantially due to the fact that the ball is out of play lots of times. So at the end, you end up with some hundreds of thousands of observations, which is still computationally intensive. But if you pool then data from multiple matches, yeah, so one could then calculate the likelihood for each match, like on a separate cluster, to increase the computational feasibility there. But yeah, I believe if you, as I just skimmed this, like if you pull data from 300 matches, then this could be really computationally intensive. So maybe it's better to fit, also for interpretation, maybe it's better to fit one model per team, so that you then for one season have like maybe 30 matches for one team. This would be better for interpretation, I guess, and this would also be better for regarding the computational cost.
What about implementation in other sports? It seems that your model can be implemented in other sports also. Have you thought about it?
So I would totally agree that this could also be implemented in other sports. It's so I've seen some kind of such analyses in basketball, at least some of these plots with these convex hull. So this is something that maybe it's already quite used quite intensively in basketball, but I think it's, yeah, totally reasonable to implement it in other sports. So for me, or for our group, it's unfortunately we do not have that many tracking data sets. So this the data I showed you here, this is also based on one match, unfortunately. So we don't have data from other sports, but if so, yeah, then one could, of course, extend this to other sports also. Yeah.
Okay, thank you very much, Marius. Let's have our first break for 11 minutes. We start again at 6:35.
Hello? Hi?